Hello, Heron and Riverside students. Last time that you were in chemistry class, you should have looked at some data, and from that data, you would have been able to predict the trends in the periodic table of elements. We want to make sure that you have the correct answers for all the trends and that you know those really well moving forward, because this will appear on a quiz next week as well as on your final exam, and this will help us throughout the rest of chemistry. So in today's video, you will learn not only the trends, but also the reasoning behind it. So when I think about the trends, I don't have them memorized, yet I can take a second, pause, look at the periodic table of elements, think about what the certain words mean, and then kind of figure out what the trend will be. And so we're going to talk through some of that and how you can find what the trends are as well. So make sure you open up to the notes that look just like this, and they are called Explaining the Trends notes, and I'm going to walk through this with you today. So the first definition that we're looking at is, what is the word that we talked about in class that is half the distance between the nuclei of two atoms in a chemical bond? That right there was atomic radii, or atomic radius. And the trend for this is it increases going down the periodic table. We can write down the periodic table, and it decreases going to the right on the periodic table. So now we're going to look at, why does this happen? Why does size increase going down? Well, we go to a new period every time we go down. And if we look at this, so what period is lithium in? Well, periods are crossed, so lithium is in period number 2. And cesium is in number 6 right there. It's the 6th one down. So next it says, when more periods are added to the atom gets bigger. Oh yeah, we think about drawing Bohr models. So again, each of these represent a period, or these are where our electrons, our valence electrons, are found. So if I were to draw the energy levels around the following atoms as we go down, well, lithium, I see it has 2 circles around it because it will have 3 electrons, because it would have 2 on the first, 1 on the next. Then sodium needs 3 shells, 1, 2, 3. So potassium, I don't have a marker with me, and it's okay if you don't draw, because I know it can be challenging to draw. That's okay if you don't, but as long as you see this right here. So potassium has 4, so it's even bigger. And then cesium would have 6 circles around it, 1, 2, 3, and would be the biggest. So we see we're going down the periods, so therefore this means that down a group atomic size increases, because they're getting bigger and bigger. But then why do they decrease across a period? That doesn't, like, when I first think about it, I'm like, it has more protons, it has more electrons. Well, since it does have more protons and more electrons, it's going to decrease going across. And why that is because when objects attract to each other, if 2 objects are attracting, so say if you have 2 magnets, if they are really strong and they're attracting to each other, they get closer together if something's attracting. Or say if you have 2 people that like each other, if they are attracted to each other, they're going to be closer. You're going to find them close to each other on a couch. And since protons and electrons attract, if you add more protons and more electrons, they will attract even more. So as we go across the period, the number of protons and the number of electrons increase. If we look at the atomic numbers, so we see 11, 12, 13, 14, we're increasing protons, increasing electrons, all on the same energy level, so all with the same Bohr model. So as we move across, the number of protons and electrons we just said increases, which causes more attractions, and the atoms get smaller because they're attracting more, and thus the atomic size decreases going across. And we see that here. So we have lithium, which has 3 protons, 3 electrons, versus boron has more protons, and this doesn't show the exact amount, but just notice that this has more protons, more electrons, so they are closer. There's more pull to them. Next, we're going to talk about ionization energy. Ionization energy is the energy required to remove an electron from an atom. And as we saw from your notes from class, you should have known that it increases to the right and decreases going down. So we have the opposite as what happens with atomic size. So if we look here, ionization energy again is the energy needed to take an electron away from an atom. If the electron is held tightly by the protons, then it will take a lot of energy to take the electron away. Again, if we're thinking of two magnets that are really tight to each other, the closer they are, the harder it is to remove it. Versus if they're farther apart, not quite attracted, not quite sticking yet, it's easier to pull them apart. So thus, if we're talking about how hard it is to take an electron away, across a period, we just talked about how the atoms get smaller, so the electrons are then closer together because it's smaller, and thus will take a lot of energy to take an electron away. So going across the period, the energy then increases for ionization energy. Now we talked about how the opposite happens if we're going down with atomic size. So why does the ionization energy decrease going down a group? Well, we got to think about it a little bit different. So as the electrons get farther from the protons, they're again easier to take away. So what would be harder? Something that's really small taking something away from it, or something that's really big taking something just like plop it off the top? Well, something that's big is farther away from the nucleus, so that's easier to take away. So when we're going down a group, the size of the atom increases. So the electron is thus farther from the nucleus, so it will take a little energy to take it away from the atom. This means that going down a group, the ionization energy decreases, as we said before. The last one we're talking about is electronegativity. And electronegativity is the ability of an atom to attract electrons when the atom is in a compound. Oh, I spelled it wrong somewhere. And for this one, it decreases going down, and it increases going to the right. There we go. So why, when we go across the table, why does it increase? Well, if we write the charges that we typically find, lithium we have +1, beryllium would be +2. You can refer back to your periodic table of elements with charges if you need to. Boron here would be +3. Carbon would be ±4, but we're not typically needing to write the charges for that. And then oxygen is -2 and fluorine is -1. So which of these are the most negative? Well, oxygen and fluorine would be. And sometimes carbon. Since there is a greater charge on the nucleus, the electron bonding pairs are very attracted to the atoms farther to the right. So the farther to the right, they are more electronegative. But then, why does electronegative decrease at the bottom of a group? You're going at the bottom. As an electron and a proton get closer, is there a stronger or lesser attraction? Well, we said as they get closer, there's a stronger attraction. Thus, as the atomic radius increases, the attraction between the positively charged nucleus and the valence electrons, we said, would decrease. So does fluorine or iodine have a greater atomic radius? So if we're looking at fluorine and iodine, well, of course, iodine would have a greater radius. We talked about that earlier. So since iodine has such a larger distance between the nucleus In the valence electrons, there is less attraction, making the atoms have less of an attraction of electrons to protons, thus they are less electronegative. And you also oftentimes can find an electronegativity chart. If I ever needed you to, later in the year, we'll talk about calculating the electronegativities between two atoms. And we can see these values. And this would never be something that you would have to memorize, but it kind of looks like the periodic table of elements. Our group 8A do not have electronegativity numbers because they are very, very little electronegativity, very close to 0 or 0. But all of our other ones do, and this is not something you need to memorize, but like lithium always has the same electronegativity, but we see fluorine over here is the most electronegative, and iodine, we see it decreases going down and increases going to the right. So this concludes our notes for the periodic table of element trends. These are things that you will need to know and decipher throughout the rest of the year, so make sure you know the definitions for atomic radii, electronegativity, and ionization energy, as well as understand those trends throughout, and we will practice more of the trends next class. Thank you so much for tuning in.